My esteemed listeners, in this video we will present the important significant application of decrease and conquer in general and DFS algorithm in particular, and this application which is widely applied in various fields of engineering and technology is coming to be called as topological sorting. We will see as to what it is. Topology means, as you must know, the way in which the constituent parts of a process or parts of an arrangement is arranged over some kind of a surface. Topological survey of India, okay, topological mapping, topological arrangement of it could be computers, okay, topological arrangement of resources, and topological arrangement of valves in a network, okay, in a water distribution network. It may be elevated water tanks, arrangement of elevated water tanks, okay, because topological sorting pertains to a graph problem, okay. Therefore here the arrangement refers to arrangement of things which have to become vertices in a graph. Of course, topological sorting is applicable only for directed acyclic graphs. It's all about plucking the vertices from a graph and arranging them in a particular order, okay. The arrangement of these vertices in a directed acyclic graph comes in such a way that if you the vertex from where the edge emanates, the edge begins, will be placed behind the vertex where this edge ends. I repeat, the topological sorting of vertices is nothing but arranging the vertices of a directed acyclic graph in such a fashion that the vertex where the edge starts is placed behind where the edge ends, and that is something like this. Let me write a figure for that. Let us say this is a vertex A, and this is another vertex B in a typical graph, and this is another vertex C, and if the directionality of connection between A to B is like this and A to C is like this, okay, and B to C, C to B is like this, so this is acyclic in nature. And when we pluck these vertices and when we place them, it should come something like this. A should come over here, B should come over here, okay, so that there exists a connectionality between A and B and A and C, something like this, okay, right. This is what do we mean by the topological sorting, okay, the definition of topological sorting, okay, right. This, as you must have guessed, this has specific application for scheduling problems, okay. The scheduling may be course and their prerequisite selection, okay. For example, in a typical curriculum, course 1 needs to be selected and course 1 needs to be completed before a student takes course 2, and because course 1 happens to be prerequisite for course 2. Similarly, course 3, in order to take course 4, I think the student must have completed course 3 and course 4. And if we draw the graph in the fashion in which the courses are taken, it becomes a scheduling problem. And then it could be construction scheduling. First of all, the earth is to be dug and it should be ready for foundation. Then foundation will start. Parallelly, we can start carpentry work, and then comes curing, and then comes construction of the masonry, something like this. And if we just attach the time taken before the completion before the start of the next event, it becomes some kind of a problem which is of a great significance. So much so that if we do topological sorting for that, and we will be able to predict by latest when exactly the project is going to be completed. Okay, these questions can be answered by doing topological sorting of the vertices in a directed acyclic graph. And two famous applications of this topological sorting, which has been designated with a different name, is called as critical path method and program evaluation and review technique. And these are all weighted graphs, of course, depicting a process in the sequence of events that appear depending on the particular problem of interest, and all the arrows, okay, going from one event to one event, or the activities will have some kind of a sequential pattern. And if you construct a topologically sorted list of vertices, you will be able to predict, okay, the latest day or latest month or latest duration by which the project could be expected to be completed, okay. And it is a problem, as I told you earlier, it's a problem of arranging the vertices of a DAG in such a way that the vertex from where a directed edge starts is listed behind the vertex where the directed edge ends. Therefore, it would seem as if we have sorted numbers, we have sorted names, we have sorted characters, okay. We have done all these things, but anyway, this is a peculiar problem wherein we are going to pluck the vertices from a directed acyclic graph, and we will arrange in such a way that there is a synchrony between how exactly project flows on the scale of time, and we will be able to predict, okay, the latest by which the problem or the program will be completed. There are two methods of doing this problem, during this practical problem, or solving this practical problem. It is DFS based method and source removal method, and we will elaborate how exactly this topological sorting is done, okay. Here is a problem. The course 1 and course 2 can start simultaneously. I'm just explaining this problem, okay, and simultaneously it will be picturized. C1 and C2 are the courses which can start simultaneously, and C3, a student can take up course 3 if and only if he or she completes C1 and C2, and C4 can be taken only upon completion of course 3 and course 2, and C5 can be taken only after completing course 4, and C6 can be taken only after completion of C5 and C4, and finally C7 can be taken by a student only upon completing C5 and C6. Therefore, C5 and C6 becomes preceding activities, and C7 becomes a following activity, and C5 in the parlance of academics, C5 and C6 can be called as prerequisites in order to take up C7. So now we will start solving this problem, okay. Once topological sorted list is prepared and a graph no more remains, and you will get list of vertices arranged in a typical fashion, okay. DFS method will be explained first, and then we will take on to source removal method. In DFS method, as per the DFS method, we need to traverse this graph, okay, in a DFS way, okay. While we traverse, we will just push the vertices whenever we visit them, and we will pop whenever they become dead ends, okay. And we have to pop all the vertices, and we have to note down the order in which the vertices were popped. Then if you reverse the order of popping, that list itself is topologically sorted list. So we will just implement this for this graph, okay, and we will see how exactly things will happen. So C1 is to be visited first, okay. C1 is to be visited first. Yeah, C1 is to be visited, and C1 will go to the stack, okay. And then C3 is to be visited, then C4, C3, C4, okay. So now C3, C4, they are to be visited, and they will be the vertices which will occupy the stack. C3 will go next, okay. C3 is the second candidate, okay, to go to the stack, to be pushed into the stack, and C1 is the first candidate to be pushed into the stack. Then goes C4, okay. C4 will go. He is the third candidate. Yeah. Then from C4 we can move to C5. Okay. We can go to C5. Yeah, C5 is the fourth candidate to occupy the stack. Right. I will write here also. I am generating DFS tree over there. And C6 is to be next visited. C6 is to be next visited. Yeah. So C6 will be pushed to the stack. C6. C6. Then comes C7. Yeah. C7 will be pushed to the stack. So that becomes a dead end. Furthermore, we cannot move. Furthermore, we cannot move. So he is the sixth candidate. Therefore, C7 becomes a dead end. So C7 is popped. C7 is popped. Therefore, this is the first one to go out of the stack. This is the second one to go out of the stack. This is the third one. This is the fourth one. This is the fifth one. And this is the sixth one. So stack gets emptied at this particular level. But there remains one more vertex that is C2. C2. Therefore, C2 will be once again introduced to this as a eighth candidate, and it is the then once again it becomes a dead end, and it is the one which is removed. Yeah, this is the one which is removed. Yeah, seventh candidate, not eighth candidate, sorry. Okay. Now the order of popping is, okay, so this is over, it will backtrack and all these things will happen, and then once again here is C2. Therefore there are two connected components for this graph. Okay, anyway, this is DFS tree. Okay, this remains to be some kind of an isolated vertex. Okay, now we will write the order in which the things are popped, the vertices are popped. Okay, and I will write it over here. It is C7, then C6, then C5, then C4, C3, C1 and C7. Sorry, yeah, C7. Sorry, C2. I'm sorry, this is C2. Then once again, this is the order in which the order of popping, let us say, okay, to simply told, order of popping. Now the reverse order of popping will be C2, okay, C2 is the vertex, then comes C1, yeah, then comes C3, yeah, C3, C4, C5, C6 and C7. Now you can see C2 to C3 is connected, C1 to C3 is connected, okay, C1 to C3 is connected, and C3 to C4, C2 to C4 is connected, C3 to C4, C2 to C4 is also connected, C4 to C5 is connected, C4 to C5 is connected, C4 to C6 is also connected, C4 to C6 is also connected. Okay, you have to show the arrows like this, okay, otherwise it becomes incomplete. And C5 and C6 are connected to C7. C5 and C6 are connected to C7. Okay, so this will give an immediate check as to whether we are doing the things correctly or not, whether we are implementing this DFS based algorithm in order to generate the topologically sorted list is correct or not. Nowhere arrow should be coming back. Okay, it should be in the forward direction only. Okay, C1 is arranged in such a way that the C1 is the vertex where the edge leaves and it joins the other vertex. Okay, it is behind C3. Okay, because edge leaves C1 and edge joins C3. Okay, this is topologically sorted list. Topologically sorted list is this one. Okay, we have to write like this with arrows, okay, indicating the directionality. Topologically sorted list. It becomes just like a list with all the vertices written side by side, just like a list, just like a vector. So this is the one. Okay, if we know the duration between C2 and C3, we can indicate over here and we can just go along the path which consumes the maximum amount of time. That becomes a critical path. This will answer one of the questions. The question is by latest on what day the project will be completed. Okay, something like this. Those kind of questions can be answered, and it is also a logical way of arranging things. Okay, in the chronological order. Okay, therefore topologically sorted list will present events or activities or whatever in the chronological order. Okay, we will take up the next problem. Okay, it seems to be very simple, but look at this. It is a DAG. Anyway, everybody should accept that this is a DAG. There is no cycle. Okay, we will implement once again the DFS based algorithm. We will go to one. That becomes a dead end. Okay, so 1 is the first vertex which will go to the stack, and 1 will be the first vertex to come out of the stack, because that forms a dead end. Then 2 will be taken. Yeah, the algorithm will visit 2, and 2 also forms a dead end because we can go to 1, but 1 is already marked for having visited. Therefore 2 is the second vertex, okay, which will go for the second time, and it will also be popped for the second time. Okay, is the second fellow to go out of the stack. Then comes 3. We can go to 3. Yeah, 3. We will select 3. Yeah, 3 is the third one to go to the stack. From 3 we can go to 2, but 2 is already visited. From 3 we can go to 1, 1 is already visited. From 3 we can go to 4, 4 is not visited. So we will go to 4. So 4 is the fourth fellow or fourth vertex to enter into the stack. But 4 will become the dead end, therefore it will be removed. So it is the third fellow to go out of the stack, and then also 3 will be removed. Okay, the vertex 3 will be removed. It is the fourth one. Therefore the popping order is the order in which, okay, the vertices are popped. Order is, we can write it over here. It is 1, 2, 1, 2, 4 and 3. This is the popping order. The reverse order is the topologically sorted list. The reverse order. The reverse order is 3, 4, 4, 2, 1. Okay, 3 to 4 there is a connectionality. Yes, 3 to 2 there is a connectionality. There is an edge in this direction, and 3 to 1 there is an edge which goes like this in the forward direction, and 4 to 2 there is an edge. 4 to 1 also there is an edge. Okay, and 2 to 1 there is an edge. Okay, this is topologically sorted list. Yeah. Now, source removal method. Okay, for the same graph we will do that. Okay, this is a very simple method, very simple method. Okay, if the graph is let us say, if the graph is very big, I think this method is very easy, it comes very easily, and we can, okay, here the method goes like this. Here the sources are removed. Source is a vertex from where only there are outgoing edges. If at all there is a single incoming edge, it cannot become a source. So with this definition, C1 is a source, C2 is a source. Okay, we can remove either C1 or C2. Let me remove C1 only because it comes in the priority order. So if C1 is removed, when we remove a source, we need to remove the arrows emanating from that source along with the vertex. So if C1 goes, what remains is this portion and this portion of the graph. What remains is this portion of the graph. Yeah. Then we can remove C2 because there are no edges coming. Okay, C2 is also removed for the second succession. If C2 is removed, this edge will go and this edge will go. So what remains is the, okay, this part of the graph, only this part of the graph. Okay, now we will remove C3. We can remove C3. Okay, C4 cannot be removed because C4 is receiving an arrow towards, okay, there is an incoming arrow, therefore C3 is to be removed. Okay, along with C3 this edge will also go. Then comes C4. C4 can be removed. Okay, removal of C4 will also take away the edges, two edges going out of this C4. Then we can remove C5. If we remove C5, two edges will go along with C5. Okay, what remains is C6 and C7 with a direction going like this, with an arrow going like this. Therefore C6 is the next candidate to be removed because that forms a source. Then what remains in the array, in the graph is only C7. Okay, the order of removal of the sources is nothing but the topologically ordered list. Okay, so C1 to C3 there is a connectionality, C2 to C3 there is a connectionality, C2 to C4 there is a connectionality, there is an edge. Similarly C3 to C4, C4 to C5 and C4 to C6. Okay, C5 to C6, then C5 to C7, C6 to C7. Okay, this is topologically sorted list. Okay, then we will try to answer some of the questions. Okay, it is a straightforward approach. Okay, we can perform the topologically sorted list. First of all, we can select it's better source removal method. If you remove the D, if you remove the D, several edges will go. Then we can remove A, we can remove B, like that. We can remove C, then we can remove G. Okay, then what remains is F and E. E will also go, F will also go. Okay, that's how. Okay, we can also try with the DFS method. Okay, by starting from A, go to B, B to G, okay, G to E, then this will become a dead end, and once again backtrack, come back to A once again. Okay, you will be ending with C to F, G is already visited from B. Okay, then what remains is D will enter separately in the second iteration of the algorithm. Okay, as a candidate to be pushed into the stack. Then reversing the order will give. Can one use the order in which vertices are pushed into DFS stack instead of the order they are popped off it to solve the topological sorting problem? This is an interesting question. Okay, this question is in the reversal of the method which has already been documented. Can one use the order in which vertices are pushed into the DFS stack instead of the order they are popped off it to solve the topological sorting problem. I think we can take a simple example over here. Let the graph be A. Okay, from A to B there is an arrow going like this. Okay, this is A to B. Then there is another vertex called C. From C the arrow is going like this. Okay, so the order in which these vertices will enter the stack is A1, B2. So B will become the dead end. So B will go, is the first candidate to go, and this is the second candidate to go, because here also there is a dead end. Okay, then stack will become empty. Then C is to be introduced into the stack. So this is the third vertex to go to the stack and third vertex to come out of the stack. So the order in which they are popped off is B, A, okay, A, B first, A next, and C. The reverse order is C. Reverse order. The question is, can we solve directly only? No, there is no way. Its emphatic answer is no, because B to A there is no arrow. A to B there is an arrow. It will be going in a reverse order. And C to A is coming like this. Therefore, there is no way of doing topologically sorting problem by just arranging the vertices in the way they are popped off. It should be reverse order. Okay, right. Then can we perform the topological sorting on the graph below? Let us see. First of all, we will choose F. In the source removal method. If F is removed, okay, everything will go. Okay, all these edges will go. So what remains is a graph A, B, B, C, C, D, D, G, D, E, E, A. So it becomes a cyclic graph. Therefore, topologically sorted list cannot be prepared, because this graph doesn't remain to be a acyclic graph. Okay, so I think we have solved the problems and we have seen to a greater detail, and this completes decrease and conquer strategy. Okay, we started from insertion sort, then we went to DFS traversal, then we went to BFS traversal, then this is the last item in decrease and conquer. Okay, so with this we will close decrease and conquer. The next session will be on transform and conquer. Until then, my dear friends, bye.